Now we have started the discussion of shear center in our classes. Just a minute before, I had to stop due to the internet problem. Now, we have discussed Euler's so far. In the last classes, we have discussed Euler's-Bernoulli's theorem, which gives us the value of the bending moment in different section of the cantilever beam itself. Now we are considered our next chapter, next portion of our discussion will be centered on the shear center. We will find out a point on the section or away from the section of a beam. Maybe it may not be on the surface of the section itself, but at a slightly deviated away from the section of the beam itself, even where there is no shear force acting. And this particular portion we defined as the shear center itself. Here we know the beam carries load, which are always transfers in the nature of axis, the nature of the axis itself. And transverse means it is perpendicular to the longitudinal axis of the beam itself. And here we always have normal stresses due to the flexion, fracture or flexure stresses, but also transverse shear stresses in any section. We have discussed in our shear force and bending moment diagram syllabus in chapter in our central material that for each section of a beam which is under the action of external force carries a shear force which is normal to the section, which is what we'll say parallel to the section itself, as well as a bending moment itself. But here, so far we have neglected this shear force as if its value is extremely small. But there are certain instances available where their shear stress may not be that small, so we cannot ignore it accordingly. And now let us have a cantilever beam here, which is embedded here in the wall, and we have a length. Its length is equal to capital L, and we are considering a section X, which at a distance X from the wall itself, and L minus X from the free end itself. It is carrying a vertical load P, which is not along the axis of the beam itself, along the longitudinal axis, but away from the axis by an amount theta itself, by an amount E. Now we have used we are now applying this three rectangular coordinate axis, X, Y, and Z, in where Y is the vertical axis, Z is the horizontal axis, and X is also horizontal, but it is not shown here. It is perpendicular to the plane of the screen itself, or it is coming towards us. Its positive direction is coming towards us. Now OX is this is the point O is called is merged with the centroid of the cross section itself. Now OX is the centroidal axis, and OY and OZ is defined as the principal axis of the section. Means it is along this axis the major or minor stress is acting, or major principal stress or minor principal stress is acting here. We are ignoring the intermediate stresses, and we know as per this major principal stress or minor principal stresses, as the definition, there should not be any shear force acting about this line itself, or acting within this plane itself. That is the benefit of principal stress. That's why we always use this position as principal stresses along different axes of our consideration. Now, due to the action of each load, due to the action of external load, we are saying how one of the load is parallel to one of the principal axis. Like say P is our load, which is away but parallel to the y-axis itself, and this load, the external load, is called the normal stress sigma, due to flexion means normal stress. This normal stress will be angled along towards us, but because in this picture it will go toward, you see, along the x-axis itself, which is shown here in the rightwards, and y-axis shown in the vertical leftwards, and z-axis is not shown. Here, x-axis is not shown. Actually, x-axis is pointing towards us. This positive direction is towards us. So, along normal stress, one normal stress sigma x will introduce along this x-axis or towards us. Shear stresses tau xy and tau xz. Due to the transverse nature of loading, there will be tau xy. Means the shear stress along xy plane and shear stress along xz plane, but no shear stress along yz plane itself, as because both are along the principal stress. So tau x and xy and tau xz due to transfer nature of the loading, and this is the shear stresses tau xy and tau z due to torsion itself. These shear stresses, there are two shear stresses will act in this section. In both along, one is xy acting xy plane, and another is acting yxz plane. But this creates the transverse nature of loading, means it is creating the bending moment of the loading, and as well as shear stresses tau xy and tau xy in the section due to torsion itself. So this type of loading itself, which is away from the principal stress, will create the shear flexural tensile stress, as well as your shear stress or torsion, or shear stress as well as torsion on the beam itself. And we have already obtained a formula. In solution, we assume that sigma x is equal to minus p into L minus x, is this distance, minus L minus x into y. It is the distance of from the centroid of the cross section towards the end, which we see that our neutral axis is passing through the centroid as a neutral plane. So P into L minus x into y divided by ij. So there is the moment of inertia ij, which is the second moment of inertia, which is along z axis, means z is along this axis itself. Means the cross section, distance of the cross section from here or here along this z, from the z direction, in the z direction itself, and multiplied by the z twice, again the direction twice, so it will have z square. The cross section area multiplied by the distance z square is the moment of second moment of inertia of the element itself. Now sigma x and sigma y and tau z is equal to 0. Sigma y is the stress along z direction. There is no force acting here because this force is vertical. Sigma y is, although we have this force vertical, but to create on other shear forces, not sigma y itself, because it is the principal stress itself. So there is no external stress here, force created along sigma y, sigma z, and the shear stress in yz plane. Then so in yz plane there is no tensile stress, the field will be created, and no compressive stress is created. This is because it is along the maximum stress, maximum principal stresses, and there is no shear stress to be created. This theory is defined as Sent and assumption itself. Now, the value of tau xy and tau yz are to be determined with the equation of equilibrium and compatibility equation. So tau yz is what we will return equation of equilibrium, and so we have to find out the preferred forces which are under equilibrium, means cancelling each other, so that there is no resultant length over our beam, and compatibility condition, which is mainly the end condition itself. The value of sigma x as given above is derived according to the flexural formula. Flexural formula is shown here, which is given as sigma x is equal to y into iy minus z into iz divided by iz square minus iz iz multiplied by mz itself. Now, the value, this determination of tau x and tau y for the general cross section can be quite complex. So we have to try. We should not try to determine this. Although it is exists at tau xy and tau z, but it is for a general cross section, the equation is difficult, so we are not going to do it. But we are one important point we are finding out that the load P in addition to bending will also twist the beam. Twist is shown here. Load is here. It is bending the beam as it is acting upwards. It is bending the beam, and as is away from one of the principal axes, it is creating twisting the beam, causing the beam as well as twist of the beam. But P can be applied at such a distance from the center that twisting does not occur. It should, what we will say, P should be at a certain distance of the tensor, means more or less close to the tensor, there should not be any twist that can occur. So we have to assume that it is more or less passing through the twist so that it cannot rotate or twisting the beam itself. Now for a section with summary, now the load has to be along the axis of the symmetry. If there is any axis of symmetry, if it's not there, it should be the central axis to avoid twisting itself. We are thinking that this section, although this section is more or less symmetrical section. So if we load applied through this center of this symmetrical axis, it will not twist through the centroid. It will not twist at all. On a section with symmetry, for a section with symmetry, the load has to be along the axis of symmetry to avoid the load crossing, which load has to be acting along the axis of symmetry, means acting along the CG, so that we should not have any twist itself. So in the same reason, a general for cross section here, the load P have to be applied at a distance E from the centroid. For a beam with a general cross section is like this. There is no particular shape, L shape, Y shape, or T shape like this, or a hexagonal or rotor circle shape, but it will have a general shape. This looks like general shape, and for a general shape cross section like this, P will have to be applied at a distance E from the centroid. Here we are applying E to the centroid with the idea that distance from the centroid is negligible, although E is not that high, so it is not twisting itself. When the load is applied to the Z-axis, when the load is applied parallel to the Z-axis, means Z-axis is parallel to it, or when a load is applied along it, like this. So what will happen? The position can again be established for which no rotation of centroidal elements of the cross-section occurs. So for centroidal elements, there is no rotation. The position should be accordingly, means there should not be any rotation or any twist of the bend. If here the load is applied along the y-axis, we can have another forces along z-axis. But in those cases also, the condition is same. It is applied at such a distance, it is negligibly small, so that it will not twist where the beam to a hard extent. No rotation of the essential element. The point of intersection of the two lines of the bending of force is significant. The point of intersection, this one, this of these two lines of bending, it's significant. So the y-axis, which is parallel to the A itself, and y-axis and z-axis would meet at a point which is although away, both these forces, not exactly y-axis or z-axis, both these forces acting parallel to y-axis and parallel to z-axis should reach a point which is important. This transverse force is applied through this point. We can resolve with two sex components parallel to y and x-axis. And note that the above discussion that this component will not produce rotation of the centrifugal axis. This point is generally called a central shear center of the flexion of the beam. So we have a force which is acting very close to y-axis, negligible distance. It will not cross any rotation itself. We can have another forces which is acting parallel to z-axis at about a negligible distance without causing a twist over the beam, or we can have, and these two line of action of these two flows say reached here, and so we have got a point here it is, and through which if we apply the inclined load and its horizontal component will go along z-axis and vertical component will go at p-axis, with this force does not create any torsion or twist over the beam itself. So this type of force is defined as this point through which this type of force can be applied is defined as the shear structure center of flexion of the beam itself. Now, here we are showing like this. This is our original, this is our cross-section under consideration of that cantilever beam. And we have y-axis and z-axis along here. And we have this point, which is negligible, distance is negligible, but it is through which we have this external load P is acting. That as the point is very close to the centroid as well as its component P1 and P2 are working very close to Z and Y axis, it is not creating any torsion itself. So the shear test center, what you say depends only on the geometry itself. That is, what is the shape of the section? Which is the general shape of the section, but actually this type of section cannot be used anywhere. We have some specific section for our practical purposes. The location of the shear strength depends on the distribution of tau xy and tau xj. So, which as mentioned earlier is quite complex, but for a thin wall beams, the approximate location of the shear centers can be determined for an elementary analysis. Here, it is also depends on tau x and tau xj, but we don't want to calculate its direction because it's too complicated. So we should find out the position of the this shear center in the next chapter, next section of our chapter itself. Now, shear center in the thin wall open section, shear center. What is this? Shear center we have already defined. We have defined a point nearest to the centroid, and if a load is acting through this point, maybe vertical, maybe horizontal, maybe at an angle. If it is at an angle, it has two components along y-axis, z-axis and y-axis, and its line of action is so close to the y and z-axis, it is not creating any twist through it as y and z-axis passing through the center. So we have to find out the position of this point itself. So here we are considering a thin wall vessel. Thin wall, you know, the radius divided by the thickness should be more than 12 or so. Means radius should be 12 times or more that of the thickness itself. Then it is called thin wall section. The thickness of the wall, is allowed to vary. As mentioned in the previous section, this thickness of this wall is allowed to vary. As mentioned in the previous section itself, the load Vy produces in general bending, twisting, and shearing of the beam. That is, what is the load here? It is the load Vy acting here. So here we are having our coordinate system x, y, and z, and this is the OC. But this is not active exactly to the CG of the beam because of its complex and peculiar nature. This beam is like a pipe, but this side is open. It is not totally complete in the cross section itself. And we are having a force equal to Vy, which is vertical nature and is parallel to y-axis, but away from it. Now, the load Vy, what the load Vy will produce? Bending, first of all, bending, it will produce, no problem. This is bending the such, this end is embedded in the wall itself. And if you apply load, it will tend the wall material, twisting and shear of the in the beam. This is like this, it is away from the CG, so it is for the twist of the beam and shear. There is also shear or vertical stress exists in all the cross section of the beam itself. Now, we have to locate what we have to do. We have to locate a point through which the load Vy should act that not to create so that it does not cause any twist. Here, Vy will not cause any twist itself. We have to locate that particular point here. That is to locate the shear center of the section. That is to locate the shear pressure of the section itself. This is then there will be a normal stress distribution due to bending and axial stress distribution due to vertical load. So, due to bending, as it is being bended this way in one concave way, the longitudinal force or force along parallel to the axis X will be created, or structural stress is created, and shear stress also created due to the vertical load itself. Then, if as a bending moment, as for each section, a bending moment is created, which is called the normal stresses, and as a shear stress is also created, which as the load is totally vertical in nature. There should not be no shear stress due to torsion itself. We are expecting the formation of torsion. Now, this subject of the film is not subjected to torsion, tangential stress, which means that the beam is open, it is don't have any tangential or circumferential stress, as we have mentioned here. As it is too thin, that is only there is no radial stresses acting here. Only the longitudinal forces acting over this, only the external forces acting over the beam itself. Now, the shear stresses near the boundary cannot have a component perpendicular to the boundary itself. So if the shear stress is too close to the boundary, this section of the shear stresses, it will not have any component parallel to the boundary itself. Next is the section shear stresses in the section near the boundary lines of the section are parallel to the boundary, but it is not creating any torsion itself. Since the section of the beam is thin, shear stress can be taken to be parallel to the central line of the section at every possible at every point. Shear stress will be parallel to the central line of the section itself. So this section should have the central line, and shear stress will act parallel to it. Say element of leg delta x, we have here this element of leg, that is delta x, at a distance x from the end and of the beam as shown in the figure of this beam. Next, this section of the beam, between this section, this is here and here, this here and this here itself. This section of the beam, it will be like this. Now, what will happen? We are having here the force structure over force condition or free body diagram of the beam itself, means we should have all the forces and balancing forces, its balancing force over the section, and we have taken a portion of the beam. It is a free body diagram, and this force condition is it is surrounding part of the original beam, which also will be such that so that the equilibrium should be maintained between the. That's what we have shown here. This is the side of the beam like a strip, and this is the end, and this is the open end. Shear stress acting along this, I mean the structural or tensile stress or structural stress is acting this sigma x here, this sigma x here. Here in this section is sigma x, and in this section is sigma x plus sigma delta x by delta x into delta x. Means this rate of change of this sigma x with a change in the section equal to delta x itself. And here is a bending moment, is along bending, it is a bending moment or from moment torque moment vector, which is having an angle towards this direction, and this moment vector, it is increased from mz to delta z by delta x into delta z, means rate of change of increase of bending moment across the z section along the changing direction of x axis. It is given in this direction. So this whole as a whole should be under equilibrium. Now, if mx be the bending moment at section x, mx is the bending moment at section x, and mz plus delta mz by delta x. And delta x is the bending moment at section delta x plus delta r. is mz is the bending moment at section x here. And in the following the same discussion, we are saying that bending moment at this section is mz plus delta mz by delta x into capital delta x itself. dmz by dx into capital delta into delta x are corresponding. So this is the bending moment, and sigma x and sigma r plus sigma delta x by dx into sigma x is the corresponding fractional stress at these two sections. So here we have bending moment, here and fractional stresses. Here is the bending moment fractional stress, but this bending moment will change due to this change in length, and fractional stress also change due to this change in length here by delta x itself. Now let us consider section S of the beam. Say this is the section S. This is a particular strip on this side of this particular side of the beam itself. It is shown here. It's defined as S. Now, this length S is the length from here to here and equal to the length of the beam itself according to these circumferences. These normal that and not non-movements with normal force is the compressive, however, consider as this unbalanced normal force is balanced by the shear force. Here you see normal force is not fully balanced, it is changed by amount. This del sigma x by delta x and del mz bending moment is also not balanced, it is changed. So normal force will be balanced by the shear stress tau xy distributing among the length delta x. What is that? Length S, unbalanced normal force is balanced to the shear force tau xy and distributed along the length delta x. The total length is there, and normal force, shear forces is distributing here, sigma tau xs. Is balanced by the shear force tau zx. It is earlier sx, yes. It is balanced by the shear force, shear stress tau sx. This is consider length. This is the length we have considered, and the additional force is balanced by the shear force tau xs created inside the surface of the beam itself, along the surface of the section itself. So what will have tau x is tx, tau sx into tx. Just 1 second. Tau sx, this is sx into ts. Ts is the thickness in the section itself.